So we'll finish off this entire chapter by introducing a new concept called the character. So it's closely related to what we did from last time when we talked about the Fourier inversion for these analysis on these compact groups. So we have this new formula. Basically, we can write f of x if f is in L2. You write it as a summation over all these equivalence class of irreducible representations. And you do the d pi, the dimension of your finite dimensional representation, and then you do the trace of the Fourier transform f hat of pi. This becomes a d pi by d pi matrix, and then you multiply by the pi x, another d pi by d pi matrix to take the trace. It turns out it should give you the value for the f of x. Okay, so you can treat this as a Fourier inversion. And so if you just look closely to this this f hat of pi pi x, so let's see what they do. So this is essentially just the trace of, let's write the f hat as the integral of, you have the f of y, and then you do the pi of y inverse dy, and then let's just move the pi x inside. All right. And what you can see is that, well, now this fy here is a scalar, so this inside complex, and the trace and the integral, they're just linear, so you can move the trace inside. So what you end up with is you can just treat it as an integral of this scalar times the trace of whatever this matrix. So here is the matrix part. Okay, so this is the pi of the y inverse x. So if you treat this as a function of g, then it looks like a convolution of two functions. So if I let chi of pi, let's say chi pi of x equals to the trace of the pi of x. All right, so then this part is just no other than the chi pi of the y inverse x. So this entire thing becomes a convolution. So this is the f convolute with this function chi pi evaluate at x. Okay, so you see this trace can be written this way. Well, so this function is very nice. Well, first of all, this trace formula, like we mentioned last time, it doesn't really depend on the orthonormal basis you pick on the h pi. The trace doesn't really change. So this, again, this chi of pi doesn't depend on your choice of the orthonormal basis. So that's a nice function. And you have this, now you have this new version of your Fourier inversion. So the f of x is essentially just equals to the summation over all these equivalence class. You have d pi times a convolution f convolute with chi pi of x. Okay, so that's what you end up with. So let's just, in this last little lecture, let's just study a little bit more on these properties of these functions. They're called the character. So definition. So I have for every pi finite dimensional unitary representation, I can define the character to be this function chi pi going from g to c, where chi pi of g is just equals to the trace of the pi x. Okay. So here I can define this, well, as long as your pi is finite dimensional, this trace is going to be pretty well defined. Okay, so I don't need to restrict myself to all the irreducible ones. But for the irreducible ones, these chi pi are going to be quite nice. So let's observe a few things. First of all, if I have a pi is equivalent to, say, pi 2, if we have two unitarily equivalent representations, then apparently because they have some kind of unitary that transfer from the h pi to h pi prime, and you can think about when you take the unitary equivalence of two matrices, their trace doesn't change. Okay, so immediately you have this chi pi is just going to be equals to chi pi prime. So again, whenever you have two things from the equivalence class of these irreducible representations, or even reducible ones, they are going to give you the same character. Okay. And so second, so clearly we mentioned the pi, this chi pi is independent on your choice of the orthonormal basis. Okay, choice of orthonormal basis on each of these h pi. So that's just a property of the trace. And finally, the next thing that's quite interesting is that if you consider what happens when you try to take the inner product of two of these chi pi. So let's say if you say let's do the integral of, you have a chi pi and you do a chi pi prime, okay, and so the let's say they're over x, okay, dx, okay, so because they are independent on the choice of the orthonormal basis doesn't mean, well, we can really choose one. So we can just pick an orthonormal basis for the pi and then pi prime. So what we end up with is basically this is just a summation, a double summation of these diagonal entries. So each of these is essentially, let's say this is summation I going from 1 to d pi of the pi I of x. Okay, so that's the trace of this pi x, and this one is summation of j going from 1 to say d pi prime of the pi prime of jj of x. Okay, there are all the diagonal entries sum up. So this becomes the double summation of this integral between basically you now take the diagonal matrix coefficients and then you do their inner product. Okay, so jj prime of x dx. All right, and because we have the sure orthogonality, so if you have two things that are not equivalent, then all of these inner product are going to be zero. Okay. The only chance you have something that's non-zero is when your pi and pi prime are unitarily equivalent. So here I should say I is going from 1 to d pi, j going from 1 to d pi prime. So if the pi is not unitarily equivalent to pi prime, then this is clearly 0. So otherwise, if pi is unitarily equivalent to pi prime, then we see that these pi I and pi jj, this inner product is equals to 1 over d pi if I and j are the same, okay, if they're the same matrix coefficient. Otherwise, the integral is still going to be 0. So you end up with d pi copies of 1 over d pi. So you this inner product, you sum it up, it should give you 1, okay? So you see that this chi pi really is an orthonormal set, okay? So as immediate corollary, so all of these chi pi is an orthonormal set. Okay, so there are kind of some orthonormal set inside the L2 of G. Of course, they don't span the entire thing because they lose a lot of dimension. All right, so we're going to see what kind of, well, it has to span a Hilbert subspace inside the L2 of G. So we're going to look at what is the subspace. So first of all, we need to do a little bit more on that. Let's just consider several basic properties. So let's do the following proposition. So in fact, these characters behave pretty well under these operations on the finite dimensional representation. So what I mean by that is that we have really, if you're given two unitary representation, there are several ways of constructing new ones. So for example, you can do the easiest, you do the direct sum. Okay, so this is going to be equals to chi of pi 1 plus the chi of pi 2. So when you take the direct sum, you're essentially just taking the sum of their character. And we also seen that you can take the conjugate. Okay, so you conjugate all the entries. This is just equals to chi of pi, the whole thing conjugate. So you conjugate the character, the function. And then finally, when you do the chi of the tensor, okay, so we have the last one is basically do the tensor product of two representations, then the character will become the product of these two pi. So we have a product of these two characters, all right? So to prove this proposition, so 1 and 2 are kind of just trivial. So you just write out what their matrix is and you look at their diagonal. That's going to be trivial. The third one is essentially I just need to know what's the trace of the tensor product of two matrices. And let me just remind you some basic facts about the tensors. So if you have say a matrix, let's say Aij, okay, so that's the ijth entry, and your B is some B of KL, okay, some let's say they're both, they may not have the same dimension really. So let's say this is n by n matrix. Let's say this is n by n matrix, okay. So the A tensor B, okay, the matrix tensor, what it looks like is the following. So there are several ways of writing this, but one way to think about it is that you treat it as a block matrix. You can say, well, this is just say A11 times the B that's occupying the first block, and then you have the A12 of B, and so on. And then here you have the A21 of B, A22 of B. Okay, so they looks like these block matrices. So here the last one, you have the ANN of B. All right. So we pretty much only care about the diagonal. So let's look at these diagonals. So what do I mean by A11 of B? Essentially, just scale the B matrix by the A11. Okay, so you have the A11 times B11, and you have the A11 times B22. Of course, off the diagonal, you also scale it by this A11 and so on. So on the first block, you scale the diagonal by this A11. And then on the second block, you scale it by A22 of B11 and so on. And then each one of these blocks, you scale it by the corresponding A. And on the off diagonal, you basically do the same thing, right? So this way, this A tensor B is really just Mn by Mn matrix. Okay, so it's so that's essentially how these tensor product can be defined. Okay. So as you can see, the trace of this tensor product now, so the A tensor B, that's just equals to the summation. If you let I going from 1 to n, you have each of these AII times the trace of the corresponding B, which is the summation of the BJJ. But this is just equals to the trace of A times the trace of B. Okay, so when you take the tensor product, the trace also multiplies. So that's from there is quite clear to see why the character of the tensor product representation is the product of the character. All right, so one more thing I want to talk about is that so because of this character, we have some really nice description of how to find something called a multiplicity. So let's just observe that if you have a finite dimensional representation, let's call it rho from B of H rho, okay, so finite dimensional representation. Because G is compact and you have a finite dimensional representation, it's going to decompose into a bunch of irreducible ones. So let's say rho is basically a direct sum of some ki times pi I, where these I going from maybe 1 to say L. Okay, all of these pi I are distinct irreducible finite representations, so they're distinct irreducible finite dimensional, of course, because your rho is finite dimensional. But the thing is, this rho is basically a direct sum, can be written as a direct sum of these. And we call these copies of these ki to be the multiplicity. Okay, so we call the multiplicity of pi I inside this rho to be this number ki. Okay, so the multiplicity essentially just means inside this rho I have a ki direct sum of or ki copies of these pi I. So as an example, we saw that, for example, the left regular representation, when you restrict it to the e pi, that's basically equals to the d pi times the pi bar. So it contains the d pi copies of pi bar. So the multiplicity, another way of saying that is the multiplicity is d pi. So it turns out that there's a really nice way of computing the multiplicity. So it's just because if you think about what happens to the character, so the character, this rho, because it's written as this direct sum, so this is really just the summation of their corresponding characters scaled by the corresponding multiplicity. So this is written as the summation of the ki times the character of these pi I. And if because all of these pi I, they're orthonormal, okay, so they're orthogonal to each other, and each one of them has norm 1. So if I want to just recover the ki coefficient, so the ki is essentially just equals to this inner product of chi rho of the with the chi of pi I. Okay, so in other words, this is the integral of the characteristic of rho with the corresponding the characteristic function of your irreducible representation, and that will recover the multiplicity. Okay, so this is the multiplicity. Okay, so you recover the multiplicity in this way, and this allows us to basically identify what kind of these decomposition it looks like. So just a quick corollary, oftentimes this is quite useful. If you consider the multiplicity, let's just use multiplicity of these identity representation inside pi times pi bar, I claim that that's equals to 1. Okay, so this is really simple. So if you want to know the multiplicity of the constant 1 representation, well, then you just do this integral. Okay, so the chi of your constant 1, well, you represent everything into this 1 by 1 matrix of 1. Okay, so the characteristic function is constant 1. All right, and so you want to know the multiplicity. So the multiplicity by our formula is equals to the characteristic of pi tensor pi bar times the chi1 bar dx. Chi1 bar is just 1, so you just ignore that. But the chi of pi tensor pi bar, that's just equals to the integral of the character pi times the character pi bar. All right, and that's essentially just this dx, and because pi bar, the conjugate is the characteristic of the conjugate is the conjugate of the characteristic, so that you have this is essentially chi pi times the chi pi bar dx, and that's just equals to 1 because we just proved if you have two things that are two unitarily equivalent ones, then their inner product is 1. Okay, or basically all of these chi pi are unit vectors in the L2 space. Okay, so the multiplicity becomes 1. Okay, so that's not something trivial just by looking at this tensor product, but it turns out using these characteristic functions, you can really compute some of these multiplicity very easily.